In this example, we're given a position vector. We're asked to find the velocity, so we differentiate it to find the velocity with respect to t, and we're asked to find the acceleration. We differentiate the velocity with respect to t, and that will give us the acceleration. So I've written down the position vector, and now I'm going to differentiate that with respect of t to give me the velocity. Derivative of 2t gives me 2. Derivative of sine 2t gives me 2 cos 2t. Derivative of cos 2t gives me minus 2 sine 2t. Differentiating the velocity with respect to time will give me acceleration. Derivative of 2, a constant, is 0, so the I component is gone. Derivative of 2 cos 2t is negative 4 cos 2t in the j direction. Derivative of negative 2 sine 2t is negative 4 sine 2t in the k direction. So we've done the first part of the question. Part B says to us, prove that the magnitudes of the velocity and acceleration vectors are constant. If they're constant, we're expecting our answers to the magnitudes to be a numerical value. So I've taken the velocity vector and I've taken the different components, 2, and I've squared it. 2 cos 2t, and I've squared it, and minus 2 sine 2t, and I've squared it, giving me, inside the square root, sine 4 plus 4 squared 2t plus 4 sine squared 2t. Automatically I can see there's cos squared 2t there, 4 sine squared 2t there. I can see that I can combine those to give me a 1. So I've written 4 plus 4 times cos squared 2t plus sine squared 2t. Cos squared 2t plus sine squared 2t is 1. 4 times 1 is 4. So we have the square root of 4 plus 4, the square root of 8, which I can simplify to be 2 root 2. 2 root 2 is a constant. So I've shown the magnitude of velocity as a constant. Now I must do the same with acceleration. This will use exactly the same technique. So I've taken the minus 4 cos 2t and I've squared it, and I've taken the minus 4 sine 2t and I've squared it, giving me 16 sine squared 2t plus 16 cos squared 2t. 16 comes out as a factor, giving me, in brackets, sine squared 2t plus cos squared 2t, which is 1. 16 times 1 is 16. Square root of 16 is 4. 4 is a constant. Hence we have shown that the acceleration, the magnitude of acceleration, is a constant. Part C of the question says prove that the velocity and accelerations are perpendicular vectors. So all you have to remember is when you take the dot product of two vectors that are perpendicular, that dot product will equal 0. So what I need to do is do the dot product of the acceleration and the velocity, and that should equal 0. It does not matter in which order I write the dot product, it should come out to equal 0. If they're perpendicular, as I've said, the dot product equals 0. So now I've written down vector v dot vector a. Looking at that, there is no I component with acceleration, so the dot product for that component is 0, so it's gone away. So the 2i is of no use to us. 2 cos 2t times minus 4 cos 2t is minus 8 cos 2t sine 2t. Minus 2 sine 2 times minus 4 sine 2t gives me plus 8 sine 2t cos 2t. We've got negative 8 cos 2t sine 2t plus 8 sine 2t cos 2t. They cancel each other out, equaling 0. Because the dot product equals 0, the velocity and acceleration are perpendicular to each other.